This video is going to talk about mixed strategies, what they are, how to think about them, and then how to solve for Nash equilibrium of a game using mixed strategies. So I have a game up here. It's just a coordination game. Think about driving left versus driving right. And I just have some arbitrary payoffs that I've put it in here. The idea being that if both people drive on the left side of the road, that they're coordinated, so they have they each get payoffs, positive payoffs. Whereas if they both drive on the right hand side of the road, they'll get positive payoffs, and things will go smoothly. But if they're not coordinated, if one's driving on the left and the other is driving on the right, then they won't be coordinated and they'll get a lower payoff that I've set to 0 here. Actually, setting it to 0 makes it nice for some of the math that's going to happen. So we've talked about pure strategies, and what we want to add in here is the idea of a mixed strategy. A pure strategy would be, in this game, these two strategies that I've laid out here. There's say drive left or drive right. They would be the underlying actions that a person would be taking in the strategic situation or the game that you would be modeling. Now, the way we want to think about this is to generalize this is instead of thinking these strategies as being chosen as one or the other, think of the person as possibly randomizing. And therefore that they're going to put they're going to play one of these strategies with some probability and the other of the strategies with some other probability. And so if there's the kind of game that you could think of as reasonably being modeled, occurring many times, you can think of these as probabilities as really proportions of play. Say the percentage of time you're going to run if it's playing football, the percentage of time you're going to call a running play versus a passing play. The percentage of times you're going to, let's say, hit and run in a given situation in baseball, or that the team in the field might maybe try a pitch out to try to catch a hit and run. So if you want to think of these as probabilities, and so think of the person, not player one, not as choosing either to drive left or to drive right, but to think of them as a probability that they're going to assign to either driving left or driving right, a probability that they will attach to each of the pure strategies that they have. Now, some of these probabilities could be 0. So in one sense, pure strategies are sort of the limiting case of mixed strategies, but that's a point we don't need to go into in a lot of detail. Now, if we wanted to think about how we get we get payoffs for each person with a given strategy, well, I'll assign a specific probability for player 2. Let's just say player 2 is going to play these two strategies, drive left or drive right, with a probability 1/2. So if they play those, if player 2 is going to choose each of these strategies with probability 1/2, let's consider how we would calculate then the utility or the payoff for player 1. And what I'll write here is this is going to be the expected utility that player 1 gets from playing left. And against the strategy 1/2, 1/2, well, if player 1 chooses drive left, then given how player 2 is playing, that they're playing each of these strategies with probability 1/2, then player 1 would realize they'd be in this cell of the matrix with probability 1/2, and in this cell of the matrix with probability 1/2. So their payoff from choosing left in this case would be an expected utility using these payoff probabilities and then the payoff in each case. So for this would be 1/2 times 4 plus 1/2 times 0. 4 and 0 being the relevant payoffs. And then if player 2 was going to choose, if player 2 chose, or player 1 chose right instead, then again, they know they get this cell of the matrix with probability 1/2 and this cell of the matrix with probability 1/2. So writing that out, it'd be probability 1/2 times 0 plus 1/2 times 2. And now, so this is an expected utility. You can just go ahead and calculate these values. And you can see that the expected utility for player 1 from choosing left would be 2. This would reduce down to 2, and then this would reduce down to 1. And so if player 2 was to play the strategy 1/2, 1/2, then player 1 would best respond by choosing to play the strategy left. So in this case here, we would be able to figure out a best response for a player. Now, if you want to figure out how you could have a mixed strategy Nash equilibrium, well, if a player is going to mix, and this is an important point, and this is one you'll need to think about a few times to get. If a player is going to mix and be willing to play each of 2 different strategies in equilibrium, then it must be the case that their expected utility, given what the other player is playing, their expected utility from the 2 strategies must be the same. If their expected utility was not the same, then they would want to put all of their probability. They would want to play the strategy that gave them the higher utility, which in this case, remember this the 1/2, 1/2. The player 1 got higher expected utility from choosing left than they did from choosing right. And so therefore, player 1 would have wanted to choose left with probability 1. They choose left for sure. The only way they're going to choose to be to put weight on both of these strategies is that they must be getting the same expected utility. So if we want to solve for a mixed strategy equilibrium, we can use that trick. We're going to use the trick to say, well, what probability would player 2 have to assign to these strategies to be able to so that the expected utility from player 1's 2 strategies are the same. So we have to do this sort of generally now, so I'm going to erase this. And we want to allow not just the probability, the strategy 1/2, 1/2. We want to be more general with this. And to do it very generally, then what we could say is, well, suppose that the probability that player 2 assigns to strategy drive left is Q. So we're going to do a little bit of algebra here. So let's call that Q. And then the probability assigned to drive right would be 1 minus Q. And then for player 1, the probability that they assigned to drive left would be P, and then to drive right would be 1 minus P. Mixed strategies are probabilities. A probability distribution, the probability that numbers have to sum to 1, and none of them can be negative. So probabilities must be between 0 and 1. The probability of any that you assign to any one strategy has to be between 0 and 1, and then between all your strategies, they have to sum up to 1. So we really only need to do P and 1 minus P, or Q and 1 minus Q. We don't need to do separate probabilities. When you give, if you say what probability player 1 assigns to drive left, then you know what probability they must be assigning to drive right. Okay, so now we're ready to rewrite these expected utilities for player 1. So if player 1 chooses drive left, they would get an expected utility of Q. They'd be in this cell with probability Q, this cell with probability 1 minus Q. So that would give them that would be their expected utility from drive left. And then from drive right, if they choose drive right, they're in this cell with probability Q, this cell with probability 1 minus Q. So that would be Q times 0 plus. And if you simplify that a little bit, don't have quite enough room here, it'd be what, 4Q And now let's do this for player 2 as well. The expected utility for player 2, if they choose left. Well, if player 2 chooses left, that's going to put us in this column of the matrix. and they would know then that they would be in this cell, the upper left cell, with probability P, and in this cell with probability 1 minus P. And if there's a payoff of 3 if they're in this cell, 0 in this one, so that would be was 3P, and then if player 2 chooses drive right, that puts them in this column. That'll put us in this column of the matrix, and then player 2 would know they'll be in this cell with probability P, and in this cell with probability 1 minus P. So their expected payoff would be 0 times P. Oops, that's supposed to be P. Okay, so we have 2 equations here for player 1, 2 equations for player 2. In this class, the only thing we'll be doing is solving for these like purely mixed equilibrium. Whenever we talk about equilibrium with a mixed strategy, we'll just be worried about purely mixed equilibrium. So what we'll do is we can use like in equilibrium, we need to have player 1 be indifferent between their 2 strategies. And so that's 4, and that's 2 minus, there's 4Q, and that's 2 minus 2Q. And if you do a little bit of algebra there with that, you can see that Q is going to have to equal 1/3. And then we do the same thing for player 2. And we have 3P and 5 minus 5P. And that's going to work out to P has to equal 5/8. All right. So that's just a little bit of algebra to do it, but you can see sort of how we're doing this in general. When you're going to solve for a mixed strategy, you have to set you're finding the probability that's going to set the 2 expected payoffs equal, and then solve for that. And then that tells you what the probability the player has to be playing. In class, we'll talk a little bit more about what this means, because there's actually a very important business and economics lesson to be learned from mixed strategy equilibria like this. But like I said, here's just a review, or here's just going over how you do the calculations. We'll talk about the bigger picture part of this in class.